All right, everybody, this is 4.2 trig functions in the unit circle. In last chapter, we talked about some general ideas around angles, how to convert between angles and radians, and degrees and radians, rather. Today, we're going to start getting into more of the behind-the-scenes math with trigonometry. So there are six trigonometric functions, and the big three that we deal with are sine of theta, cosine theta, and tangent of theta. And they also have, inverse functions. They're known as the cosecant of theta, the secant of theta, and the cotangent of theta. So these are our six trig functions, and they're defined by their relationship to the sides within the right triangle. So what do I mean? The sine can be found by using the opposite over the hypotenuse as a ratio. The cosine is the adjacent side over the hypotenuse, and tangent is the opposite over adjacent. Right, these functions are ratios of side lengths within a right triangle. The reciprocal functions are just that. So the cosecant is going to be the hypotenuse over the opposite side. The secant will be the hypotenuse over the adjacent side. And the cotangent will be the reciprocal of tangent. It will be the adjacent over the opposite. I know we worked with these before, but these are just kind of a quick refresher on how all these interact. So based on some pieces of information here, we can give, if I know two sides of a right triangle, it's possible to find all the different pieces of this triangle. So let's make it a right triangle here. Let's make one of our legs 4 and our hypotenuse 5. Well, we have a right triangle. We may need our Pythagorean theorem to find the third side. That third side is a leg. So we can say 4 squared plus b squared equals 5 squared. I have 16 plus b squared equals 25. So b squared equals 9. B would equal plus or minus 3, but we have a side length of a triangle here, so the positive is the only answer we really care about. Well, now that I have all three sides, I can very easily find the ratio of all six trig functions. I think it's worth it right now to pause your video and try to find those ratios as fractions of those six functions we just defined up above. Sorry, before we do that, we also need to define which angle in question is the angle that we're defining as theta, the reference angle. So in this case, we'll use this bottom right angle as theta. So go ahead and try to find the ratios of all six functions. And here it is. So what you'll see here, pretty straightforward, same idea of what we did up above, just putting some more solid numbers to things. My expectation is that we are extremely consistent identifying these ratios. So we can keep moving here. We also have a relationship from a right triangle. We find that co-functions of complementary angles are equal. This sounds like a very fancy rule, but let's just investigate what this means. So let's say I have a right triangle here, and we'll make this side theta. That would make this our opposite, this our adjacent side, and again, hypotenuse our longest side. So this angle, well, I'll color code it. This angle here is 90 minus theta. I know that from our triangle sum. I know that all three angles must add up to 180. So this angle is complementary to the theta angle. What that means is that the opposite and adjacent now have changed roles. So if the opposite and the adjacent have changed roles, then sine and cosine have kind of changed roles. So that's how we make sense of our co-functions of complementary angles. So the sine of one angle in a 90-degree angle is the same as the cosine of the other angle. The tangent of one angle is the same as the cotangent of the other angle in that right triangle. This should make intuitive sense, but these rules are useful and we will see them throughout the course of the unit. Now we can move on to everybody's favorite, the unit circle. So the unit circle refers to a circle of radius 1 with its center at the origin. This is really helpful for us if we know the radius. We always know one side of any right triangle we create with this unit circle. So the side lengths represent X and Y coordinates. It's a nice way to move back and forth between triangles in kind of abstract geometric space and triangles on the coordinate plane. So let's talk a little bit more about this unit circle. Suppose an object travels a circular path, and that path has a radius of 1 unit. So if we're moving along our unit circle, that 1 unit represents our radius. This position along that curve can be represented in 2 ways. The distance along a curved path, we call this a radian. Right, that makes sense. Part of a circle. And then the number of degrees around which we've rotated, here's our degrees. So for this reason, we're going to use radians and degrees interchangeably when we talk about our unit circle. So what we're going to do here is we're going to fill out our unit circle as best we can. I'm going to fill out the top left-hand corner, and then we'll kind of jump to the next piece. So let's start with what we know. Well, if I know that the unit circle is 1 unit away, then I know the coordinates on the outside are going to be 1, 0, and up here, 0, 1. Everything else is going to be based off of a special right triangle. So this will be a 30-degree angle. I'll make one here with a 45-degree angle. These are reference angles. And then finally, we'll make one with a 60-degree reference angle. Well, from our past, we know, let's fill in what we do know. We know that the radius is 1. And what I know in a 30, 60, 90 triangle is that the longest side is twice as long as the shortest side. So if I know my hypotenuse is 1, I can figure out the shortest side across from my 30-degree angle to be 1/2. And that the intermediate side is root 3 times as long as the shortest side. So now I have all the coordinates I need. So this is a 30-degree angle. Oh, sorry, I missed some other key pieces here. This exists at 0 degrees, or 2 pi if we go all the way around. This first angle we're dealing with as we work through our first quadrant is 30 degrees. In radians, that is pi over 6. The coordinates are going to come from the right triangle that we just found, this 30, 60, 90. The x coordinate is going to be that bottom, that root 3 over 2, and the y coordinate 1/2. Now we can move to our 45-degree angle. I know if the radius is 1, that its side lengths are, I have to divide 1 over root 2 in order to find the side lengths. So if I were to rationalize this, I would get root 2 over 2 for both lengths. So root 2 over 2 are going to be my coordinates for my 45 or my pi over 4 location on my unit circle. And then for my 60-degree angle, or pi over 3, I'm going to have basically just the opposite, the coordinates of what I found on the 30, 60, 90. My x coordinates are going to be 1/2, and my y coordinates, root 3 over 2. What else did we miss in the first quadrant? Well, this is a 90-degree angle, and in radians, that's represented by pi over 2. So I'm not a big memorizer. I think you guys know this by now. My recommendation as you look at this is just get comfortable with these special right triangles. We don't need to memorize anything if I can construct any of these points at a given moment. There's certainly a lot of different ways to keep things in mind. Some people will use the sequential nature of these numerators on the y coordinates, you can see that it's really the square root of 1, the square root of 2, the square root of 3. There's a pattern that's developing. And then to finish out the other 3 quadrants on our unit circle, all we need to know is how our angle measure, our quadrants work with signs. I know in the second quadrant, I'm gonna have a negative x value and a positive y value. I know that in my third quadrant, it's gonna be negative and negative. And in the fourth, it's going to be a positive x value and a negative y value. The measures themselves, the reference angles we're using here, are going to be the same, right? So this 120 degree or 2 pi over 3 angle is going to be very similar to the 60 degree reference angle in the first quadrant. The only thing that's going to change is the x coordinate is now negative. The same will be true on our 45. Well, now we end up at 135. 3 pi over 4, and now we have negative root 2 over 2 and positive root 2 over 2. The last one here, and then I'll let you all finish the rest, is going to happen at 150 degrees, or 5 pi over 6. Again, we're going to have very similar looking coordinates, just one element. In this case, the x coordinate has become negative. So what you'll notice here is that we have the same triangle, right, in 2 different quadrants. You'll notice there's a strong relationship between their coordinates. We could find the other coordinates at the bottom of the screen. I'm going to pause it. I'm going to let you guys fill in as best you can. And if you're not sure, you can always pause and check my work. All right, so take a look. Here is our full unit circle in all its glory. We can see that, sure, there's a lot of information here, but I don't want you guys to be overwhelmed. I want you to see kind of how it all fits together. I'm going to do some highlighting here, but what we have is we have 4 different reference angles. These all make 30-degree angles with our x-axis, right? So what we should notice about all 4 of these is that their coordinates are very similar. All that really changes are the signs. So these 4 points, right, in our first, second, third, and fourth quadrants are all behaving relatively similarly. The same is true for our 45-degree reference angles. You'll notice them in red, and I'll highlight them as well. Ooh, that's not a highlighter. So if we were to highlight these 45-degree reference angles, they are all going to behave the same way. We know that those 45, 90s are isosceles right triangles, so that the x and y coordinates magnitude, their scale will be the same. We'll just have some differences on signs. Finally, we have our 60-degree reference angles, right? You can see they are all closest to the y-axis. And use your common sense with these coordinates as well, right? If I'm looking at a 60-degree angle, it is taller than it is flat, right? So the y-coordinate should be bigger than the x-coordinate, right? Understand that we're still dealing with coordinates. So if I am the furthermost towards the y-axis, that's going to lead me to a relatively or comparatively small x coordinate. So I think we're going to pause there as the unit circle, and then we'll talk about some other functions in part 2.